All right, so in today's class, we're going to look at two things. One is the second principle of thermodynamics. Okay, something that is more or less the same thing comes from the second principle of thermodynamics, something that is called the TdS relations. Okay, so far, what do we know? We know that the first, so recalling, the first principle of thermodynamics which is what is heat minus work equal to the change in energy. Okay? Or let me rewrite this, or let us rewrite it as delta E, where if you want the partial of the work will be PDV, but that's not the important part in this part. But the important part here will be that delta Q is more or less equal to Q, and from the entropy equation, so last time we saw what was the entropy. So what is the entropy? Entropy, we had that change in entropy was equal to what? Was equal to the change of heat divided by a reference temperature. Okay? And what do we say was a good definition for the entropy? We say, if we want to make it simple, it's a variable or quantity or property that let you estimate how well you're using the energy, no? If you are not wasting energy, then the change of entropy is zero. If you are wasting energy throughout the process, then we say that because of the principle of increasing entropy, the delta S should be a value positive, no? Different than zero. All right? So now, from the second equation, so now what I'm going to say is combining. So basically, I'm going to take this equation here, what do I have? From this one, I can find that delta Q will be T delta S. So we have we're going to get T delta S minus the work equal to the change in energy. Okay? And this equation here is actually what is known as the second principle of thermodynamics. So basically what did we do over here? We changed the heat by the entropy. So if you remember, if we use this equation, what were the two deficiencies of the first principle of thermodynamics? Is that, let's say, the change of energy through a cycle was equal to 0. We say that this means that Q equal work. That means that you can transform other heat into work, or you can recover other heat from the work. So we say that that equation, having Q equal to W, implies that the process is 100% efficient, and that it could go in both directions. However, what do we know? We know that because every single process needs to happen between two different temperature reservoirs, a cold and a hot, okay, the efficiency can never be 100%. Okay? That was one of the limitations. And the other limitation is that we know that some processes, when you have the equal sign, they cannot go in both directions. It can only happen in one direction. And the variable taking that into consideration is the entropy, okay? The delta S. So this is the equation here that we have for the second principle of thermodynamics. Okay, where over here you want delta E is the change in internal energy plus the change in kinetic energy plus the change in potential energy. All right? So this is the form of the second principle of thermodynamics, but generally is not used under this form. It's used under the form that is known as the TdS relation. Okay? So what happens is that in most cases, the way this is used is, let's say, page 78. All right, so let's say neglecting kinetic and potential energy effects. What do we have? We have the expression, so the expression TdS T delta S minus partial W equal to change in energy. So neglecting potential kinetic energy, and let me put it here. Recalling, I put on the previous page, I don't want to redo it, that the partial of the work will be equal to PDV. What do we have? This equation here is going to reduce to T delta S minus PDV will be equal to the change in internal energy. Okay? Just did this equation here. If we neglect kinetic and potential energy, we're just left over with the internal energy. Okay? Okay? Or I can write T delta S equal to change in internal energy plus PDV. Okay? Okay, so the above equation, maybe I should have done that before, but it doesn't matter, can be written as what? So the only thing I'm doing is change the delta S, basically is the same as taking the differential, no? For small change, so TdS equal to du plus PDV. Okay? And let's say this will be our equation A. So now let us try, or let us write the above equation using the enthalpy. So let's see, what is the definition of enthalpy? Remember, enthalpy we say is internal energy plus the term work done by the pressure, PV. Okay, this is the definition of enthalpy. So this is just mathematics, but let's see what happened. So if I take the derivative of dH, what will that be? It will be, the derivative of the first one will be du. And now what is the derivative of two functions? You first keep one constant, it will be, and you change the other one, so it will be p dv. And then the other one will be what? This time you keep v constant, and you're going to vary p, no? vdp. It's like the derivative of the function uv is u prime v plus uv prime, no? Yeah, so this is the same thing. All right, so from this equation, what do we get? We're going to get that du will be equal to what? dH minus pdv minus vdp. So now what I'm going to do, I'm going to substitute this du over here into du over here. Let's see what we get. So substituting a, so little lowercase a into uppercase A we're going to get TDS equal to what? DH minus PDV minus VDP plus PDV. So here you can see right away that these two terms are going to cancel out. We end up with the second relation, the second TDS relation, which is TDS will be equal to DH minus VDP. Okay, so now basically our two general TDS relations are going to be expression A and B. So you see guys, this is starting to get complicated, no? So 79, so the two general TDS relations are TDS equal to du plus PDV, and the second one is TDS equal to DH minus VDP. Okay, guys, so let's see. We go back to this equation here, beginning of the class. This equation here, first principle of thermodynamics. What was the initial equation that we wrote down probably about 75 pages ago? What is the name of this class? Thermodynamics. No? So what was the starting equation that we used? We used summation of forces equals to MA. Correct? Yeah? From the equation summation of force equals to MA, we rewrote that equation to the form of work and energy. Alright, but the initial equation was summation of force equals to MA. So what I'm trying to say is that these two equations here, this is summation of forces equals to MA. So it doesn't look at all like summation of forces equals to MA, no? But the starting point of everything we have done so far, that was the equation. So this is equivalent to summation of forces equal to MA. Okay, so here I just want to point something out. It's true, 90% of the cases you can use this in 90% of the cases, but so far, what are the two types of systems we have been dealing with? We say, like, if you have a closed system, so in this case you have two cases. You can have something which is en bloc, no? Which is just a closed volume, all right? But what's characteristic about this one is that the mass was constant inside. So this was the type of system. And then the other one is called open system, open slash control volume system. And the definition for that one was basically that so in this case, this was your system. In this case, this is your system. All right? And in this one, what you had is mass flowing, okay? M dot, you have mass flowing through the system. Okay. So, again, this is true in 90% of the cases. So if you are dealing with this type of system, what is here the equation? What is something specific about this one here? Is that the volume is constant, no? Yeah? So then what would that mean? That dV will be 0, no? Okay. Now, what is the other case that you can have? You have this one. In this case, if you have a piston cylinder and nothing is affected, what is the characteristic of a free piston cylinder assembly? Is that the pressure will be constant, no? The volume might be changed. So if you want, generally, in 90% of the cases, because always some exceptions, these closed systems, if you solve a system about closed system, what is the equation you're going to have to use? Use the equation TdS equals to du plus P dV. Okay? Now, obviously, I think you probably can't guess what I'm going to say next. If you have an open control system, in this case, what is constant? Your control volume is constant, no? Yeah? So for this type of system, you will have to use the TdS equal to dH minus V dP. Okay, because what was the H? Was U plus the work of the energy, no? I mean, if you remember when we did the derivation for this type of system, we use H equal to U plus PV, and we substitute the U plus PV by the enthalpy. So if you want to remember which one goes with which one, try to think about this. It's true 90%, more than 90% of the time. All right? Okay, so all right, let me just do this now. So the general TdS relation are generally written for specific quantities. So for example, what is specific in thermodynamics? What does it mean? Is that we use the lowercase u is equal to what? Specific internal energy, no? Lowercase v is equal to what? Specific volume, yeah? And the lowercase h is dh is h over m. This will be the specific enthalpy. So these are the specific quantities. Okay, so we use this one. The TdS relation can just be written as TdS, and also you're gonna have the lowercase s equal to the capital S over the mass will be the specific entropy, will be TdS equal to du, and this is the way you will find it most of the time in the book, plus P dV will be equal to TdS equal to dH minus V dP. Okay, so this is general TdS relation using specific quantities. Okay, guys, so somebody pointed out to me, and you're absolutely right, this should be a lowercase h. This is the specific quantity. Thank you for that. This is the lowercase. All right. Okay, so page 80. All right, so ideal, what I like to call ideal substance assumption is what? So the ideal substance assumption comes from the fact or the term ideal gas. So what is something specific about an ideal gas? Is that the gas, an ideal gas, remains a gas all the time. It remains on the same state, no? So we say that the assumption of ideal substance basically means that you can have a substance like water that can change states from liquid, gas, or solid, no? But maybe in the process, it's always going to remain between the same state. All right, so the ideal substance assumption is that a substance remains in the same state and remain the same state. And I'm just going to add this, and far enough to be valid from the saturation lines. Okay, that might now sound confusing, but as soon as I'm going to do the figure, and it will be clear. So So let's say it doesn't matter if I do the TV or the PV, okay, that doesn't matter. Remember we're having this curve over here that will say here this is a gas, this is a liquid, and in the middle will be a mixer, no? All right. This line over here, if it was a pointer here, this line over here was called what? Saturated gas. And this one here was called saturated liquid, no? So what am I trying to say with that? The assumption is going to work best if you are far away from this line. So what does that mean? Is that if you're going to be a gas, you're going to be as much of a gas as possible, no? Because the closer you're going to be here, you're not going to be 100% a gas. Does that make sense or no? So what I'm trying to say is that you need to be as far away in this direction to be a gas. Can you be a mixer? No way. You can never be a mixer, no? And if you're going to be a liquid, what you want to be is as far as possible from this saturation liquid line. Okay? And in those cases, the ideal substance assumption will work best. But if you are close to this saturation liquid line, so saturation gas line, probably the assumption is not very good. Okay? Okay, so what are the ideal substance assumptions? So ideal substance assumptions is the same thing as we did for the ideal gases. Will be what? The specific internal energy will be equivalent to what? I mean, I hope this is clear now. Internal energy is related to the C sub V, no? What about the enthalpy? Will be related to what? What was the other one? C sub P dt. Guys, be careful because well done, but this should be clear by now, okay? So we know this. And then what is the other assumption that we have? The ideal gas relation, which is PV equal to RT. So these three are the ideal substance assumption. And from this one, okay, I do it now, you can rewrite what? You can write that, I think we're going to need P and, let me see, we're going to need P and V, yeah. So from this one, we can write that P will be equal to what? R T divided by V. And from this one, we can write that V will be equal to R T divided by P. So let us substitute these assumptions. So let us substitute above assumptions into the general T ds relations. Okay, so let me rewrite the TDS relation. What was the TDS relation? We had TDS equal to du plus PdV, and TDS equal to dH minus VDP. Alright, so now I'm going to substitute this du, I'm going to replace it by CVDT, this dH by CPDT, this P by RT over V, and this V by RT over P. Okay, and see what happens. So what I'm going to get now is, you guys see the page here. And this. So what I get is TDS for the first one. DU, we're going to replace it by CV dt. Then we're going to replace P by RT over V. So this will be equal plus RT dV over V. And the second one will be TDS equal to CP dt minus RT dP over P. Okay, so next, what I'm trying to find is what will be the change in entropy. So if I divide both sides by T, what do you get? You're going to get ds equal to CV dt over T plus R dV over V. For the first equation, for the second one, ds equal to Cp dt over T minus R dP over T. Okay, the next thing we're going to do is to integrate. So this will mean what? On this side you're going to have, oops, should have done a little. So it will be ds between S1 and S2 will be equal to CV integral of dt over T plus R integral of dV over V, and this will be, if you want, since upper limits of integration, T1, T2, V1, V2. So this will be for the first one. And the second one will be ds will be equal to Cp dt over T minus R dP over P between S1, S2, T1, T2, P1, P2. So if you do the integral, what do you end up with? You end up with S2 minus S1. What is the integral of dt over t? Would be the log function. Okay? It will be plus, so it will be CV log T2 over T1 plus R log V2 over V1, and then the second one will be S2 minus S1 will be equal to CP log T2 over T1 minus R log P2 over P1. Okay, so over here, all this stuff is to do what? I know everything starts to get complicated. All this stuff is to try to find out what is the change of entropy, because the change of entropy is 0, we know it's reversible, but if it's not equal to 0, we find out that it's irreversible, no? So now we have two relations to calculate the change of entropy, no? So instead of writing delta S2, instead of writing S2 minus S1, let me just rewrite these two equations as delta S, so the change of entropy will be equal to CV log T2 over T1 plus R log V2 over V1, or delta S equal to CP log T2 over T1 minus R log P2 over P1. Okay, so now what do we have? We have two expressions for what? Change in entropy, but this is only valid for what? For ideal substances. Okay, so if you look at the problem we did last time in class, okay, you see that we had no idea about these equations, correct? However, what did we do? Let's see what was the problem. I think it was the problem where we mix water, no? We did the problem that we mix hot water or cold water with warm water, and then we'll see what we get. So let's see, what did we do last time? So remember last time we solved the problem. Let's say we have a container, we have cold water 15 degrees Celsius, hot water 80, you open the valve, the two waters are gonna mix, no? We got water at a temperature of 52.14 because we had 3 kilograms of the 15 Celsius and 4 of the 80, no? And then we say, okay, once you mix the water, can you get the water back 1 at 15 and 1 at 80? No, so this means that this process is irreversible, meaning that the delta S needed to be equal to 0. As you can see here, what I did is what? I did basically the same thing we did today. This equation, this one ds, dv we know is 0, okay? So you see, you don't need to memorize the equation. You can go very quick, so this is 0, TDS, you divide by t now, and we ended up with this expression, correct? This expression here, for the closed system, is exactly the same as this one over here, no? Yeah? Okay? So, I mean, you don't really need to memorize this equation. To me, it's faster to just derive them very quick. And that's what we did, and at the end, what did we find out? I think that the whole thing at the end was, you see, MCV equal MCV T final over T1. This is not for specific quantities, but you use a specific quantity. That's why you forget about the M. And what do you find over here? So this is the T cold. So the cold water was gaining energy, saying that the entropy was positive, but the hot water will be doing what? Losing energy, no? So we obtain a negative value. But at the end, when you add both of them, you should end up with a positive quantity. And this positive quantity is kind of represents, first, that you did not use properly the energy because you wasted energy. And this kind of represents what is the amount of energy that you cannot recover. All right? That's what we did last time. All right. So today, I just formalized everything by deriving those two equations. But what I want to say is that you don't need to memorize them because they can be derived very quick for every specific problem. And that's generally what I do, okay? Every single specific problem, I just go and rederive it because that way I know what I'm doing. I don't like what I call the cooking engineering, saying that I need to solve a problem. This is the equation I need to use. Let's just go and substitute, no? Okay? You need to understand what you're doing. All right? So, okay. So there's one more thing here about this equation, and it's when we have to deal with ideal gases. Okay, so let me see if I can show where is the problem here. I'm not going to get into too much detail because I think I'm just going to make it more complicated. I'm just going to give you the information. If we go to the tables over here. All right, so let's see some tables. We can get to the tables. A4, I guess, page down. All right. For the ideal gases, this is not here. This is water, so you're not going to have it. This is still for the water. Okay. So for the ideal gases, I don't know which one it is. Is it? I'll find out which one it is. I think it's T20 or something like that. So this is still liquid. This is a refrigerant. We're not going to have it. Ideal gases. After all this, I don't know which one it is, table A16, we should be getting closer. Superheated propane, no. Okay, so it will go 820, I guess. Ideal gases, specific heats. All right, so over here you see for ideal gas properties of air, you have some quantities here that are called P sub R, V sub R. We'll see what this R, P sub R, V sub R will be later, okay? But right now, you see here that you don't have the S. You have an S with an upper little 0 or O, no? Okay? So what does that mean? Basically, you need to go to these tables. This is temperature. This is enthalpy. This is internal energy. And this will be entropy, no? Do you see that the entropy is not really the S? It's the S with the upper letter 0, and so on. Okay, so let's see what that means. All right, so for ideal gases tables, the quantity, which is the entropy S upper sub O is defined. So what is this quantity? So the definition of that quantity will be S sub O will be equal to Cp dt over T. Okay? And from this equation here, all right, and from expression, really it's a combination of this one here and this one over here, okay? All right, basically these steps over here. We have integral ds was equal to what? Integral of Cp dt minus r dp over p. This is same as this expression over here, no? Yeah? Okay. So if we integrate this one, what do we have? We have that this is S2 minus S1 will be equal to what? You see this quantity here is equal to this quantity over here, no? And this is, so this becomes S sub O, S super O at T2 minus S super O at T1 minus R, and once you do the integration, this will be log P2 over P1. So basically means that now if you want to find the change of entropy that happens into an ideal gas, what's going to have to happen? You're going to have to find these values here from the table, no? Yeah? And it looks to be what? Table what? Table 822? Might be more, but let's say from table 822. Yeah, it looks like it's table 822, 823 maybe. Okay, 822, 823, something like that. 822, 23, okay, maybe some more, okay? Hold on 1 second. For table 822, 823, and some more, you get this one from the tables, but you will have to calculate this one to find the total change of entropy, no? So have the total change of entropy, total change of entropy for an ideal gas is what? Delta S will be equal to the minus R log P2 over P1. So we'll have two different quantities. And I don't like to do these problems, to tell you the truth. Because you need to go look these ones on the tables, and then you need to do this calculation for the pressures, and then you need to add again each one of these ones. Okay, so like I said at the beginning of the class, this is the last part I want to cover before the second exam, and now the rest of this class and the next two classes I want to concentrate on the exam 2, no? Okay? Because I think you only have the exam 2 basically is the same as exam 1, plus you will have to use the tables, And in addition to have closed system, you also have open or control volume system, no? Okay? And this program might require some work, all right? So let me pause for a second. I'm gonna try to do some problems. All right, so just like I was saying, let's try to do some practice problems. We only have about 15 minutes, so maybe let's just look at this one, okay? Problem 441. All right, so problem 441. Take a new page. Oops. 441, but page 83. All right, so let me do the figures. Refrigerant. Let's see if I can do this. I don't know how good it's going to be. Probably not that good, but let's try to do it this way. So let's say refrigerant 134A, which is the product you have on your AC system in the car, generally enters an insulated compressor, also in a steady state. All right, so what is a compressor? Compressor, generally, doesn't matter how you sketch it, you can just do a triangle, a rectangle and say compressor, but generally the figure they use for compressor is what? You compress, no? So let's say you have this, so let's say you have one on top, one on bottom. Like the front of an engine, no? You compress the air. So let's say this is a compressor. We know it's working at steady state. So if it's working at steady state, what does it mean? Is that the amount of refrigerant going in is the same as this amount of refrigerant coming out. So you have in, out, refrigerant 134A, and this is probably getting at a mass flow M, no? And you're going to have this mass flow in equal to the mass flow out. What else do we know? It was something saying insulated. If it's insulated, what does that mean? No heat change, no? Okay? So this is important when you solve problems. You see, I spend a lot of time doing this because I need to give me time to think about the problem. So refrigerant 134 enters an insulated compressor operating at steady state as saturated vapor. Okay? So what do we know? Here this is saturated vapor at minus 26 degrees Celsius, and a volumetric flow rate, which is AV1, equal to 0.18 cubic meters per second. Refrigerant exit at 8 bars and 70 degrees Celsius. So I'm going to have that. So this is 1, this is 2, P2 equal to 8 bar, T2 equal to 70 degrees Celsius. Changes in kinetic and potential energy from the inlet to the exit can be ignored. All right, so let's say this can be ignored. We need to determine the volumetric flow rate at the exit. Okay? So determine part A, AB2, and looks like part B and the compressor power, and B compressor power. So the compressor requires power in order to function. So how much power is needed in order to run this, okay? Okay, so I think part A is pretty simple. I mean, it's not simple, okay? I have a lot of practice in this, okay? So basically, what's important over here is to know that the steady state assumption, I mean, I already read it, is going to imply what? M1 will be equal to M2, no? Yeah, remember it was a conservation, basically conservation of mass. The amount of mass going in is to be equal to the amount of mass coming out. Maybe next time I do a problem when that is not the case, okay? Just in case you know how to do it. All right, so in this case, what would be M1? By definition, the mass flow M1 is equal to the volumetric flow rate divided by the specific volume. So in this problem, we know what is AV1, the volumetric flow rate. Can we find what is the specific volume? We need to know two things, no? Do we know two things? We know the temperature, and we know the state, okay? So let's see what would be the table we need to go to in order to find that. So it's minus 26. So I think we passed them, the refrigerant 134, I know which one it was. But I guess it's stable. Let me know when you see refrigerant, okay? Ammonia, saturated ammonia. Superheated refrigerant, so that's not the one we want. So probably stable A, let's see. Is that refrigerant? That would be good. Refrigerant, we can go to awesome, minus 26. We have at least the value, we don't have to interpolate, okay? And we know it is saturated liquid. So that means we need to look at what? V what? V gas or V fluid? We need to look at V fluid, no? So we can say, remember this will be the 10 to the 3 will mean this value has been multiplied by 10 to the 3. So that means that from table A10, come right here, table A10 at T equal minus 26 degrees Celsius, V sub 1 will be equal to V fluid, which is equal to 0.7265 10 to the minus 3 cubic meters per kilogram. All right? So guys, again, my mistake. The problem states here saturated vapor. I don't know why I went to a saturated liquid. No. So this is V1 equal V gas 0.1882. Okay, cubic meters per kilogram. All right, since we have here more or less the solution that they want us to find, let's see what were the units they looked at in, okay, cubic meters per second as well, no? So let's go and check, see if we find the same thing. So now, knowing this and knowing that M2 equal to M1, M2 should be equal to A V2 over V2, yeah, specific volume, which will mean that the volumetric flow rate at the exit will be equal to the mass flow 1 times V2. Okay, now, do we know two things at state 2? Yeah. So we can go to the tables and find what's happening there, no? So we know P2 is equal to 8 bars, and T2 equal to 70 degrees Celsius. So let's see what's happening in there. So let's say we go to the one of the tables, 8 bars. What is the saturation temperature? Is 31.33, no? So what does that mean about the state? It's going to be to the right of the curve. It's going to be superheated. Yeah? Okay? So we need to go to the superheated table. So you can say here T2 higher than T saturation. So means it's superheated. Okay, that's what I put over here. T2 higher to T saturation, which is, we're going to find out on the table again, but 8. So the T saturation, hopefully we have an 8 over here. Okay, here we go. C saturation was 31.33, no? So we need to go to table A12. So say table A12 at P equal 8 bars and T equals 70. Hopefully we have 70 over here. Awesome. What do we have for V2 will be 0.03131. 0.03131 cubic meters per kilogram. Let's see if we can finish it. So now, finally, what can we say? Finally, A V2 will be equal to M1 V2, which should be equal to what? I never calculated that one. Okay, so it will be equal to what? V1, so M1 should be equal to what? AV1, which is 0.18 cubic meters per second divided by V1 that we find equal to 0.1882. So if you want, let me put here, this will be equal to AV1, sorry for that, divided by V1 times V2. So this is equal to AV1 times V2 will be 0.03131. So hopefully, please go and check. But if we didn't do anything wrong, which I don't think we did, you should get, I'm going to give it to you, 0.0299. Can you go and check? Is that what you get?
Yeah.
Okay. So 0.0299 cubic meters per second. Okay, so if you want next time, we keep going problems from the assignment, right? We finish this one, just remind me, and we keep moving on. Okay, guys, start working on this homework because the exam probably will be based a lot about this, okay? I mean, I already prepared the exam, but...
You want the questions?
And